Okay, for this, we're going to find the electric potential of a uniformly charged disk. So, as we can see, we can have a point particle a distance of z away from the center of the disk, and we have a disk of radius r. And so the task is to find the electric potential V coming out from this charged disk. And so the first thing to do is to consider what a differential segment of this area, of this disk field. And so one way that we can do that is by defining what's known as a charge density, or sigma, which is defined as an infinitesimal charge divided by a tiny area. Okay, so rewriting, we have dq equals sigma dA. And so to find the differential in the area, we know that the area of the disk is just pi r squared. So dA would just be 2 pi r dr. But in our case, since we need to find a differential of this ring, we're going to introduce a new variable omega. And doing integrate from omega when it's 0 all the way to r. So we can equivalently write this as 2 pi omega d omega. I'm going to clean some stuff up for you here. So we have dA equals 2 pi omega d omega. We have dq sigma 2 pi omega d omega.
We also know that electric potential is equal to KQ over R. So in this case, we have this R distance, which is right here, would be equal to the square root of omega squared plus z squared, because like Pythagorean theorem. And then in this case, our electric potential would be 1 over 4 pi epsilon naught per k. And then the integral from 0 to r of this dq over r, which would be omega squared plus z squared. And then if we plug in what we found for dq up here, then you get 1 over 4 pi epsilon naught integral from 0 to r of, which way is this supposed to go? Sigma 2 pi omega d omega, and then over omega squared plus z squared.
Alright, so now to perform the integration, we can take out some constants to make it easier for ourselves. So we can take out sigma 2 pi also because it's not dependent on what we're integrating. So we can say equal with sigma 2 pi over 4 pi epsilon naught, which just becomes sigma over 2 epsilon naught times the integral from 0 to r of w over the square root of w squared plus z squared dw. So in order to integrate this, we can use something called u substitution. So we can say that u is equal to w squared to make this integral easier. So what we could do is differentiate both sides, so we get 2w dw equals du. And now what we can do here is we can isolate dw on one side. So we get dw equals du over 2w. So now we can plug this in for dw, but also since we're making the substitution, we have to make sure to change our bounds accordingly. So our bounds would now be, we can plug in our bounds to find our u bounds, so it would be r squared. So we'd be integrating with r squared when it comes to the u part. So when we plug in our u, with 0 to r squared, this constant comes down, of w over the square root of u plus z squared, where z is a constant, times du over 2w. So the w's cancel out. And now we have a pretty simple integral where we have u plus z squared to the negative 1/2. And we have this constant stuff outside. So this is going to be u plus z squared to 1/2 times 2, or divided by 1/2. So that, notice when we have the 2 over here, when we divide by 2 and we multiply by 2, those cancel. So in the end, we're left with r squared plus z squared, the square root of that, minus the square root of, when we plug in 0, we get z squared. And this equals the square root of r squared plus z squared minus the absolute value of z. And then times the constant that we have. And that would be our electric potential.